This math investigation is about grid mazes. I define grid mazes as a maze with consecutive numbers where the grid is made up of square units and you have to get from a starting point to an ending point. With this math counts problem, you have to move from 1 to 7, going up, down, right, or left. No cell can be crossed more than once. We had to figure out what is the greatest possible sum. This math counts problem came up in one of the math counts booklets that the kids and I were working on. So as we were going through the different ways to get from 1 to 7, we realized that we always had to skip one number. So in my mathematician's notebook, I worked along with the students, going from 1 to 7. You can see that in my first attempt, I skipped the number 4 and got the sum of 60. I noticed that since one number always had to be skipped no matter what maze pattern I used, I then realized that I had to skip the lowest number, which was 2, in order to get the greatest sum of 62. Then I started to ask, well, what if the square was bigger? Would it follow a similar type of pattern with skipping a number? So I tried a 5 by 5 grid, following the same consecutive number pattern, getting from 1 to 9 this time. And I realized when I did the maze, I didn't have to skip a number. So the greatest sum was all of the numbers added together, which was 125. And that also was an odd number. Looking at another even by even square, I did a 6 by 6, following the same consecutive number pattern. I realized that I actually did have to skip one number in order to get from 1 to 11 without crossing any cell twice. My greatest sum was 214, which was even also. Looking at a 7 by 7 grid, I was able to get from 1 to what is now 13 without skipping a number. So my greatest sum was 341, which was odd. An 8 by 8 grid, following the same sort of pattern, I was able to get from 1 to what is now is 15, and I did have to skip, again, that number 2. So in the even side length squares, 8 by 8, 6 by 6, and 4 by 4, I did have to skip the number 2. And I skipped the 2 since it was the lowest number in order to achieve the greatest sum possible. So I looked at the sums of 4 by 4, 5 by 5, 6 by 6, 7 by 7, and 8 by 8 to see if there was any sort of sequence between these sums. And after looking at their first difference, second difference, and even third difference, I was not able to find any sort of pattern within the sums. So my conclusion for this part of my math investigation was that squares with even numbered side lengths, I needed to skip one block, and the greatest sum was even. Squares with odd number side lengths, I can reach the end point and hit every number, and also my greatest sum was odd. So now with my next part of my math investigation, I took the opportunity to use a problem posing strategy from Brown Walter and asked, what if the shape was not a square? So then I looked at rectangles. Looking at my mathematician's notebook, you can see that I used an even and odd side length 4 by 5 and an odd by even dimensions 5 by 4, and I was able to get from my starting point to my ending point. Since numbers were not really a factor for me anymore, I drew the rest of the mazes without numbers since I was done with calculating the greatest sum possible. So now I looked, since an even and an odd and an even, I was able to get from the starting point to the ending point. And I even checked it with another even odd pair, a 6 by 5 and a 5 by 6, and realized that this was actually just a reflection of the other. So it would make sense that an even by odd and an odd by even would have the same result, which is that they can get from the starting point to the ending point without skipping a number. I checked an even by even rectangle, a 6 by 4, and realized I did have to miss one block when getting from my starting point to my ending point. The starting point and ending point in all of these mazes also stay consistent with lower left and top right. Looking at another even by even, I looked at a 2 by 8 and a 4 by 10 and realized in both of these cases I had to skip a block in order to get from the starting point to the ending point without hitting any of the other cells twice. Then I looked at an odd by odd and realized I could get from start to end in both a 3x5 and a 5x7. So these ones were able to work from start to finish. So with the rectangles, it looks like an even by odd dimension worked, also odd by even. An even by even did not work, meaning it could not get from start to finish by hitting every block. You had to skip one. And then an odd by odd dimension did also work. So I gave myself another question dealing with what if not, and said, what if the starting position was not in the lower left corner? So this is where my next part of my math investigation continued. I moved around the starting number and I kept the numbers the same, just focusing on the path. So looking at the path, I can see that now I'm starting with a 4x4 grid, which is even. And I now place my starting point at position 2 in row 1. I'm just going to deal with row 1 in this math investigation. Position 2, I was able to get from start to finish without skipping a block, which is very different from when it started at position 1. When I tried it with a 5x5 grid, which is odd, I started with at point 2 and had to skip a square in order to get from start to finish. In a even number, I started with position 3 this time. In the 4x4, it did not work in position 3. I had to skip a square. And with the 5x5 grid, in position 3, I did not have to skip a square in order to get from start to finish, so it did work with the odd number. My position 4 worked with the 4x4 square. My position number 4 did not work in the 5x5 square. And then position 5 in the 5x5 square was able to work from start to finish. So with that part of my math investigation, I noticed that when the squares were an even side length and the starting position was in an even space, 2 and 4, I was able to go from start to finish without skipping any cells. In the odd number side length, if the starting point was at 1, 3, or 5, I was able to get from start to finish without skipping a cell also. Then I started experimenting to see if I could figure out a 14 by 14, a much larger square, if it was an even squared, based on what I have concluded, how many ways could I get from start to finish? How many starting points could get me from start to finish without skipping any blocks? Since this is an even numbered square, I would be starting at 2, 4, 6, 8, 10, 12, or 14 as the starting point, and I would be able to get from start to finish. And I did test it a couple times. You can see my lines here, getting from each point to the end. So then with even numbers, it looks like if you divide the side length by 2, that is the number of different starting points that you can get from start to finish without skipping any blocks. I realized that I can do a lot with what I defined as grid mazes. There's a lot of different ways to investigate. And instead of spending more and more time on this, I decided to leave you with a couple of things that I would do if I was going to continue this math investigation. One of the things I was considering, what if the ending point was not in the upper right-hand corner? So I could experiment with different starting points and ending points. Number 2, how many different paths can be traced from one point to another? So looking at unique patterns of getting from one point to another. And is there a pattern between the number of ways there is to get to the ending point and the size of the square grid? The third point, what if the grid was another shape? So we could have shapes with 8 sides, with 10 sides. We can have a dodecagon. Looking at ways we can, different patterns with different shapes of grid mazes and how their different properties can compare or contrast with the square grids that I investigated in this math investigation. And that's where I'm going to leave you with today, with my math investigation with grid mazes.